So I'm Frank from University of Baltimore. My research topic is a collaborative framework for detecting advanced persistent threats. This is my research overview. I'm going to talk about introduction, which cover what is advanced persistent threat, and its current solutions, and the motivation to our research. So basically, our approach is to design a collaborative framework to detect APT. Finally, I will summarize my research. So, introduction. First of all, what is APT, which is Advanced Persistent Threat? APT is a state-sponsored cybercrimes. For example, some organization could replace malicious code on your computer for specific stealthy tasks. There's many current solutions has been proposed. There are many folks on analyzing log files. There's two type approaches. One is static approach, another is dynamic approach. For static approach, that analyze or scan a signature of some files. And dynamic approach, they're analyzing the behavioral pattern of APTs. The problem is all those proposed approaches, they act alone. So for example, they set their own environments, they collect the evidence, they observe signatures and patterns, they make their own conclusions based on their judgment. It's quite difficult for cybersecurity communities to verify recreate their environments, verify their observations, and reuse the observation results for their own research. So we focus how to detect APT more effectively. So our approach is to come up a collaborative framework for detect APTs. We focus on two aspects. The first one is collaboration. So we want to share cyber forensic evidence intelligence. And the second, we want to come up a dynamic detection algorithm which utilize the shared cyber forensic evidence intelligence to monitor a system under investigation dynamically. So the first challenge is how to share cyber forensic evidence intelligence. And well, why share cyber forensic evidence intelligence? Well, sharing is a critical strategy to solve problem. It allows us to avoid missteps of their peers. Also allow us to deploy proven detection solutions. There's two questions we have to address. The first is address the legal aspect of digital forensics. And the second is the cyber forensic evidence intelligence formalization. So the legal aspect of digital forensics, many focus on traceability and validations. It has a lot of questions we have to answer. The first is, where is forensic evidence collected? So is those evidence collected from memory and disk? We have to keep tracking those evidence. Second, who does collected evidence? The third is, how does an analysis process carried out? And the last is associated with the validation, which means how does above processes and results are validated. So we have to make sure all the tools used for collecting evidence are validated. we need to make sure the analysis algorithm steps are validated. For traceability, and we need to extend, our approach is to have forensic evidence to extend current cyber threat intelligence, which is proposed by other organizations. Basically, we try use this diagram. This could see as a class diagram, which is an idea borrowed from software engineering. And we want to use this class to describe where the tool, what are the tools used for collect evidence, and where those evidence collected from, those media class, and who does the investigation, and how evidence preserved, and what are the algorithm used for identifying those forensic evidence, and how to interpret those forensic evidence. For evidence formalization, and we focus on how to discover those evidence and organize those evidence so it can be formalized in nice way. And also we need to discuss the information expression. So this is overall architecture we try to discover and organize the forensic evidence. So there's 4 layers of architecture. The first layer is crime cases, or the crime. So all the crime cases such as virus or child pornography, or some IP violation, it's described as scenario. This first layer. Second layer is we treat the computing related device as an evidence generator. So we further divide the evidence generator into 3 different categories. It's like hardware layer, and operating system layer, and application layer. So every layer, we treat those are evidence generator. The layer 3 is the evidence category. So we further refine those categories into subcategory. For example, for application generator, and actually that could be further decomposed into 2 categories, which is app function generated evidence or app non-function generated evidence. App function generate evidence means those evidence generated by functional requirements of the system. And app non-function generated evidence means this evidence are generated by non-functional requirements of the application. For OS generated evidence, we can further, similarly, we can refine those into subcategory. And for hardware generated evidence, we can refine those as such as memory or non-valid memory generated evidence, so on and so forth. So layer 4 are a list of forensic evidence objects. So for information expression, we're going to extend STIX, which is STIX calls structured threat information expression, which originally designed for shared cyber threat intelligence, and we extend STIX to express forensic evidence intelligence. So here's one example. Let's assume we are using, this is one of the objects, and we formalized in a JSON file. So for example, so this is one type of cyber forensic evidence objects. So it's kind of, this is describe one virus. So this is created date, modified date, name, description, also files. So the highlighted here indicate the tools used. The tool is used for collectors evidence and where the evidence saved to. For example, this saved in disk, and the disk is manufactured by Samsung. And investigated means who conduct investigation. All those information is a description of those class diagram we mentioned earlier. And the results of those information formalization, we save everything is in a repository we call Cyber Forensic Evidence Intelligence Model repository. And so basically, if this is a list of objects, we have to formalize in repository. And the second question, how to utilize cyber forensic evidence intelligence to monitor system and investigation. And actually, we will discuss this state machine we're going to use. So we extend a finite state machine, and we using forensic evidence. So that we call this state machine is forensic evidence driven finite state machine. So abbreviation. So we call it FASM. I'm not going to spend much time to describe a state machine. Every state machine has a set of states, a set of transitions. However, we're going to focus on the guard condition. So this guard condition actually is a collection of logic expression. So it's a first order logical formula which can be evaluated as true or false. Okay, so I'm going to give one example. So this fast state machine model describe the behavior of system under investigation impacted by poison ivy. The poison ivy is a remote access tool used by many APTs and cyber criminals for information infiltration, means they try to steal information. So to model this system under investigation impacted by the poison ivy, we come up 4 states. The first are secure states, which indicate initial states and indicate the system has not been compromised. And penetrated states indicate some malicious code, virus code has been executed on the SUI system under investigation. And exploited means the SUI, the system under investigation has been exploited by attackers, APTs, to gain a better understanding of the environments for future actions. And exfiltrated indicate the system has unauthorized movement of data. So those 4 states. The transitions between those 4 states is indicated by I just come up 3. First, phase 1, phase 2, phase 3. And actually, each of those ID here has a lot of the guarded function, has a combination of comparison expression. So let's take a look at those comparison expression. So here I list 9 comparison expression. For example, the first one just indicate the name of the poison ivy server. So that's indicate that's executable file. The second comparison expression or pattern we can say is the created file. And the third one is a created folder. The fourth one is running process. And also this indicated registry key for auto run. And here is IP address, subset of IP address, networking traffic, and this is the port number. So the condition of transition basically is subset of those comparison expression. For example, if for any of the states, if match one of those comparison expression is true, we know these, like from state, there will change of current secure state to penetrated state if one of those conditions or patterns is matched. And for second guided condition, they say if in exploit states, and if there is some patterns, like if pattern 7 repeat 10 times within 10 seconds, means from exfiltrated state, we change the state to exploit state. So basically those guided condition make transition from one state to another. So the next is we call a threat activity detection engine, which is actually, I make this should be this from here. So basically the detection engine compare whatever the evidence we evidence indicate, like the shared cyber forensic intelligence we see, we collect from other system. And also we will have collect observed data, means which is we collect our log file. The citing algorithm actually is one of the we call threat activity detection engine, and we compare the results between intelligence and the data we collect from our log file. We make a conclusion. It indicate there's any threat activity going on the SUI. So here is deploy diagram for data APT. So here is it's called a cyber forensic intelligence client. So everyone can upload their intelligence to server. So there could be many clients submit their information if they want to share to the server. And also, if for any organization, we can download those shared cyber intelligence into their own machine. And also we're going to come up our own state machine, and such as FedFM state machine. And then we're going to using the shared information and our state machine. And also we're going to take the evidence which collect from our SUI, and this is our threat analysis detection engine, and we using the engine to detect is there any APTs. And now here our finite state machine, we are using an open source called Squirrel Foundation, which provide basic finite state machine function. So those is our implementation. I put this implementation on the GitHub, and those is the diagram generated based on implementation. Now conclusion. So we come up a fat assessment model, to which the model are driven by real world knowledge of adversary tactics and techniques stored in shared repository, which is we call shared cyber forensic evidence intelligence. And we use algorithm or patterns to indicate or monitor the APT status by analyzing the forensic evidence that malicious actors left on the digital device. So this approach requires systematic collecting crime activity logs and extract evidence from those logs and formalizing the digital evidence. And so we define this approach defines two types of digital evidence. One is shared evidence and observed evidence. And so this approach can be used for detecting other cybercrime if we be able to collect evidence and also using download the shared evidence from the other server. So here, if you have questions, and send me email, and I will happy to answer the questions. Right. So this is my presentation.